Меня зовут Станислав Смышляев, компания Cryptopro, коллеги Сергей Агафин, Евгений Алексеев. И наш доклад посвящен обсуждению.
So I have my colleagues here, and we're going to discuss a number of items that have become quite painful at the practical security conferences about the cryptography in Russia. There are very many perceptions that we can hear and argue both online and offline. It's a set of kind of myths. Some of them are true, some are not, and related to the fact that all the cryptography in Russia is obsolete and 25 years old, solution-based, it's slow, system issues with sustainability, and our overseas colleagues sometimes making very strange publications support these myths. And the strange perception is that in Russia, all the cryptography is rather, paper security oriented, but not is paper based, bureaucracy based, but not providing real protection. So we would like to share, probably discuss, and we would like to have a constructive discussion, not mythological. So why is it of concern to us? Many partners and integrators believe in a set of myths and cliches, and very often they use a scheme when they use foreign algorithm, when in the lines with the highest load they use RSA or AES. And when they need to certify, they provide the FSB certificate, which is less secure. And very often, as we can see, it contradicts the ideas of real protection. And the other consequence, quite painful, is that very often, say half a year ago, there was a case when at a conference on practical security, there was a presentation about some Russian cryptography solutions, and the criticism was not constructive. It was kind of bookish, which is probably not good, because the real vulnerabilities, multiple insecurities and risks are what we'd like to address by experts in practical security more attentively. And as a result, the practical security experts have lesser tools as all Russian cryptography is being discarded. The cryptographers have a very strange, dubious reputation. They have to prove themselves from scratch that they are good. They have to prove there are no vulnerabilities, and in spite of information about real threats, there is a number of cliches that does not give you anything practical. So let's talk about this sustainability. Probably the sustainability of our block codes, and after the Courtois attacks. So after the ISO committee hearing, so there were 4 or 5 articles which claimed in small fonts and comments that nobody reads comments, but the numbers remain in memory. So he actually, if you consider his work in detail, and he also admits that it's Courtois where that says there is no sustainability issue. I cannot spend too much time. I'll give you the link, and there is an article with the Courtois analysis, quite a comprehensive one. And this is an example, a print screen of his slide from a conference that says that he ignores the data complexity and just compares the running time. But in the comments and mass media messages, we see only numbers.
And the other question that is there is it's a very well thought out attacks, and this is Isobe and Dinora Dankelman Shamir. And not going into detail, so certainly there is a certain level of robustness and sustainability, but there are real attacks which brought about the possibility to organize such attacks. But if the rules of the use of the script to encryption to use it properly, so then these attacks cannot be launched if the encryption is properly done. Certainly that's so. Then if you need to verify the algorithm, you need just to check for this algorithm for its robustness, and then nothing will happen. But the robustness of the encryption so will be a good guarantee against any attack. So the old hashing function situation is bad. And because the old hashing function, so there were two successful attacks, and for finding collision and looking for another image, so that's the damage was quite considerable. And even now, we introduced the new hashing standard function, and we issued there's a new document so how the system should be migrated to the new standard. So the document reflects that, and all companies need to move to a new standard. Is it a good standard or not? And so the standard for robustness is quite. A lot of work has been done, especially recently, and so there were some at the Federal Security Service. So there were a number of tenders and bids, and actually the work that was presented to them for their attention. So that it was quite robust things, and so they sustained all the attacks, and so the Federal Security Service was happy with that. And then so what actually specialists of the Kaspersky Laboratory were talking about, that the state authorities they need to select constant to make it bad. But Altavi Yosov spoke to the extent that the stream for using this constants may result in reducing robustness. But our colleagues from the state authorities, so they were saying that that all constants that we have in Stribog, so they are the images of another function. So getting something so cannot be proven by arbitrary iteration. So selecting the constant, if there is some vulnerability, so you cannot select those constants that would fit in like keys. It's not possible. Now the state authorities are attempting to justify that the offered solutions are not so allegedly not robust enough, and because so there are some bugs in every algorithm. So then electronic signature is quite straightforward. Our electronic signature for robustness does not differ from ECGCA, so it's the same. And although this, so someone criticized the selection of elliptic curves for robustness, but the guarantee of arbitrariness of one-time values in the process of signature, so it's quite good. So because we need to remember this, the vulnerability of 2010 in Sony PlayStation 3, so I had the problems in the realization of ECDCA. So where the constant was put in, so instead of arbitrary values, so that certainly reduced the robustness. So, but at the same time, so it is comparable to the American standard ECDCA. Then efficiency. So we know that they say that our standard is better than ECDCA. It's not true. So then so you can see here the implementation as a Bernstein OpenSSL implementations. You can see different, and this is the state standard. Is pretty much the same level. So depending on the architecture, it's pretty much the same level, comparable level of strength. So then certainly we have. So comparable speed is pretty much the same, and what we have, so IS will be 6 times more reliable than GHOST, but that's not because we are we complain about the standard, but it is the standard. It's not the cryptography. Cryptography is fine. So then, if we show it on a chart and show it in a graphic manner, then GHOST is quite good, and so it's even better than IS, and as far as its robustness is concerned. And but hash functions, comparing so the new SHA-3 standard, so our GHOST is a little bit behind, but pretty much the same. And we even better than the second candidate for ASH3, and so then it's even better. So this we fare pretty well. About the signature, so the ACDCA, so the speeds are the same. So they have the selection different fields and elliptical curves, the algorithm of signature, so you can compare them with NIST SP 857 or RCA. So this our GHOST is compared to their standards, comparable to their standards, and so we are somewhere in between RSA 7680 and RSA 15316. Then checking. So our GHOST is at a good level. So then validation of the signature validation, and so it's quite good. So but in the event when we talk about deforming the signature, then GHOST is much better than RSA, and much more than it is better than ECDCA, and because when you form a signature, RSA does not have any points like, so there's a good open key, so they use the arbitrary random parameters, so that certainly gives a better speed compared to the elliptical curves approach. So then random numbers. Then what do we do with our state standards, with our GHOSTs, if we encrypt using an open key? So because we don't have our own key, but we have a solution that was reflected in the recommendation of the State Standard Committee, Technical Committee, which addresses this issue quite successfully. So they generate a key, and so with the recipient key is used in this procedure, and then it's encrypted with the key that's encrypted in another system. So the Diffie-Hellman system. So this encryption, which is an open key. So hashing. So it's related to so then to use the system many times. And the time required is the same as the time that is required to check the validity of the signature. So pretty much the same time frame. So then the Russian GHOSTs are quite good, robust, and So that was done in many solutions. And now the relationship between the security on paper and the real security. So what are the main paper laws that would so then it's a requirement of Federal Security Service of Russia to cryptographic means and to encryption means. And so then personal data is open. It's not secret. This order. So I'm going to quote from that instruction. So what they criticize a lot is that the specialists they not relate. They don't know what cryptography is, and because the violations are not they're not just related to the real paper, because it's a paper is important, and so the security, so there is a model on paper only, but not in reality, so they do not guarantee so the same security when in a combat operation. And so there is a certificate, and but certainly it makes people unhappy, and then so it has to do with the certification system. Then in others, the requirements are confidential, and so the engineers have no chance even just to see what F1, F2, KS1, KS2. So like quote from that order, KS1, it's not a secret order, to comment how the real security is related to the security that they allegedly have on paper. And the KS1 is attacking outside the controlled zone. So meaning the attacks against cryptographic protocols via network. And so we need first to protect ourselves from a bad guy, a miscreant just who tries to attack protocols outside, not in-house. And so just to set up certain systems means that would protect or just to or preclude the access to the hard drive from outside. Then case 3 level, when the user has an access to the computer but has no access to the account of the user, and so they can attack from another account, from under another account. And so this is the idea was just to stop this unauthorized access. So that's why we can see that what they declare is different from what they actually, the level of security that this system provides. Unfortunately, so there is a difference. Then where the keys are kept, stored in real systems. So this a passive. So for example, it's at the end of the day, it's just a memory stick, or it's an active autonomous calculator, or it's a functional hybrid solution. So it's a functional key carrier, and or passive carrier. So then it's put on the protected secure channel. So then the passive carrier. So they use after login, it goes to the card. So after logging, so the memory on the card contains the cryptographic stored memory, and the key is always in memory. Then in case of active token calculator, after you do the logging, so all the operations are made on the token. So which one is better, which one is worse? So they criticize the first solution to the fact that it's possible with the help of technical means to intercept the token if there is a bad guy trying to do that. But again, if so then you can just counterfeit a signature. So with the help of this machine, if you have an access to this machine once, then you can counterfeit, you can doctor the signature. And if you have an access to the channel between the machine and the card, and so for example, if we remote operation mode, and so then there is a certain so an NSB port, then in some cases so the key can be taken out after the first attempt to hack the system, or after the first login. So the miscreant has a password, and then he can just add any data he wants. So that is why I say the authenticity of the key disappears. And so using the key, but it's possible to hack anyway. So in case of active calculator, so then there's a problem. Then there appear more serious issues. So on a small card, so they calculate so the elliptic curves, and that takes time, very lengthy procedure. And then if you don't implement it correctly, so it can generate a number of problems related to the leakage of adjacent channels or side channels. And whatever you do, so the access to the channel goes through the encryption of the key. So formally, we and when you start asking, so why this solution is used in the system, and this is not an argument, and it certainly makes people are so that this means should be used only if the perpetrator cannot get an access to the channel, but irrespective whether the token is active or not. So then there's another more advanced solution whereby so first we need to protect a secure channel, secure between the token. So first you identify the channel, and as you generate the key, and then in securing the key, you do certain things. So thus you have a secure key, and then the question, but it's very easy just where to do the the operation. That's an I/O function, and this is possible using KS3. So then KS3 is very easy for any user. Is there a chance for a perpetrator to get access to the channel? So can you possibly protect this channel if it goes through the unprotected, unsecure zone or not? And so to use the key, the signatures correctly. So I hope that this example demonstrates then formal KS1, KS3 reflect the difference between the level of security of the system, and so but this is only the top of the iceberg because the level of security is different. What else is part of the notion of so-called cryptography is secured at different levels, high level, low level, and so about vulnerabilities. So we have analyzed the following issues. So the basic cryptographic algorithms, tuning the concomitant cryptographic algorithm, vulnerability of cryptographic protocols, vulnerabilities when you embed the cryptographic algorithm. A few years ago, we could have said, so then theory is not related to robustness of the system, and because but now at TLS, Beast and Poodle, so there will be no threats like that because so the attacks of Beast and Poodle in clear form were described and very well as a theory. Barden with the nail theory at conferences as theoretical attacks, but no one paid attention that they can materialize, so these threats and attacks could happen, and then the majority of the servers are not protected in any way. So what are the mistakes? What is considered that will not be considered in cryptography? What mistakes are not considered? So for example, so low-level cryptography mistakes. So incorrect use of block regimes, CB, ECB, CBC. Then appearance of side channels, So if the mechanism of padding is not used in a secure fashion, and so they can be easily so intercepted by the gauges of rhythm that calculate rhythm, or covering the gamut of frequencies, or using the synchro messages without guaranteeing the terms of their random nature. So the unpredictability. So TLS related, so they're sending this, as was saying, in case of their unpredictability. And if the key load is higher, then the key can take it. And so CBS and CFB vulnerability. So if for every new package in TLS you do not use a good, unique, random synchro package, so you'll have a hole. And Gregory and Bart in 2004, they were talking about it. No one listened. No one paid attention. And then the Dong and Rizzo so became famous in the whole world in 2011 when they conducted successfully this attack. And if IV can be controlled by the perpetrator, so then selecting one block byte by byte, bit by bit, so then can easily so identify the encryption text. So then a small advertising to Russian cryptography before those attacks in Russia. So in TLS Russian algorithms approved by TK26. So they adopted this new so gamma type mode operation, and no one could break it. So the ciphering encryption machine so operated quite well. And so that's right. So even if the perpetrator tries to hack into the system, then the most important components of the encryption, so that bad guy cannot hack. Then, so for example, padding. So if you are not working with padding correctly, so because this is the a set of byte constants, pad len, before the end of the block, where pad len is a number of required padding bytes. So then the perpetrator through the channel, or on the other side of the channel, you can launch an attack. Exactly what was proven in 2014 when this attack was launched. The idea is that, and so each byte of each block can restore so almost all the text without reading the key. So 128. So over the last, but before, so sometime earlier, before this attack was committed, 12 years earlier, so it was described. This attack could have been possible, and so this challenge when our TLS spoke about this is TLS version 1.0 for the users of CBS sets of encryption was described many years ago in 2001. But if you take the same TLS with gammating, so in order to be able just to work with packages, so then it even aggravates the problem. For the robust crypto system, IND-CPA, robust system, so you cannot use the same package that opens up into a gamut and with the context twice. So that could be a good example. So then you know this example. So comparing between the real and so then the imagined one. So you can see that this one minimal gammating. So then covering the gamut, covering the gamut, or overlapping the gamut, covering it. As if you take, for example, so this block diagram of this encryption system, if someone starts to send so packages, so then the perpetrator can get this without any key. And so this is obvious that certainly so kills all security issues, and this is the problem that we needed to address, and so our partners face this issue when we talk about embedding so good means but by bad ways. So naturally, when you implement this, so we check these issues, and so we need to make sure that this works. And then another point, so is the key load. So every cryptography people know that you cannot use so the encryption 64 64 length and more than 32 gigabyte of information. Otherwise, so one will adversely affect the other. So no longer than 64 bit key can be used. Otherwise, it will be overloaded. And so 10 megabyte is an optimum load. And if you want to work the key correctly, so then the load should be no more than 7 megabyte. So these solutions exist. We know how to realize the keys, how to work them, but there is a big problem. So how to work with the tokens? So that's to give no more than 10 megabytes per key, and that is why we should not do it so off the top of our head. And so we need just to certify this and develop it properly, to standardize it, to make sure that the system works, and to check it for robustness and sustainability. And so such solutions, so they take the key, they duplicate it many times, and then do the same thing on the key copies. So the copy, the key was just duplicated, reiterated, and so then in our instructions we speak about that. So the key tree implementation. So it took time to put it together, but now it works well. In order to generate a low-level key, so because so the speed it doesn't slow down, but the realization is more difficult because we have selected the algorithms, and there are recommendations of the technical committee, and so the keys have been analyzed and algorithms have been established. So how can you, should we relate it to the authentication or not? And because in real life we can use even not the hash function so much, but if it has an embedded vulnerability, even related to, so on MD5 you can use our signature as a second attempt to create an image of the second image, so then is reduced to 2 raised to the power 128, and which is only 5 orders of magnitude. And as you know, then so the attack related to the certificates of Microsoft, so discussion is still going on. So we don't know whether MD5 was hacked or not. And but one way or the other, so the main problem lies someplace else. Main challenge is that if you use this kind of system, authentic code system, which is signature, and in the system, Windows system, you check. So then similar procedure with the variability of algorithms is used by Microsoft authentic code. So then with some additional attributes, so you do a good hash, and
So with a good, it will be hashed and then signed. So the bottom tier hash, something crippled, then on top it will be cached by nice algorithm. So where is the catch? the one who signs has no issue because the probability this source code can be faked is next to zero. So this, well, has some properties. Absolutely unpractical. But the checking party interests, well, is deceived because he is giving the wrong information, but which is another thing. So with a practical attack to build a manageable collision, if we select a PDF or deja vu format with the opportunity to compile, whereby you can add a check and replace values. So if they create a collision, those values, you can create two documents which will be reflected differently, which is unacceptable. Because PDF is permitted to use. And in Russia, legally, you can only use 3 hash signatures. The first pair is going to be forbidden after 2018. So, but in real life, if you use the third standard, so you apply. And then the last thing I wanted to mention is try to convince you that many solutions in Russia do not have any tags and there is no catch and there is a good solution, the author thinks. The most popular issues that Snowden discovered that is disclosed to be discussed among cryptographers, that's a tag to do with the numbers gadget. So the logarithm of a point was known to A and B. So the attacks that are possible, but and there is an argument that proves that that's not like that. So it's not the only argument that's used. So the parameter, each candidate for the parameters is calculated as a hash from a random line. Then you check that the parameters comply. If not, then you take a different value. So if we believe in hash, we believe in parameters because the structures of hash and elliptic curve are different. You cannot compare them. So in our standards, Russian standards, in ROS standard, we have that, and you can believe in our curves and parameters, and the signature is the same as the American one. You cannot do much about it. And then, briefly, I'll tell you that there is a set of ways and algorithms and the functions of random data and diversification are very similar to the American ones, and that's if you don't like to use an out-of-the-box solution, this is a recommendation to use our standards in IPsec and in CMS and TLS. And that it can be used, and all the justifications have been provided or described by the standard. And then I will pass the floor to my colleague about the practical goals. Thank you, Stanislav. I would like to tell you about some practical tasks that the cryptographers address when they develop protection, how the keys are stored and what solutions can be offered to businesses, how those keys are generated and how these solutions can be embedded into life systems. So let's start with the tasks. So the bottleneck in any system that's going to use cryptography is working with tokens. And sometimes you need unconventional solutions that will allow you to minimize the number of use of such devices. One signature is about a second, so if we have an operation like that in a flow, it can eat up computer resource and other things. And then speaking about the password, on one hand, you want to make it safe and ask a password for each operation without remembering, and our life is different, and a common user that would be using KS1 tools do not want to see many offers, and they want to simplify this task, and for them cryptography is rather a burden but not security, and something that is being forced on them. So not to lose the users, we want to support this attitude and still providing the high security. So speaking about synchronization, speaking about cryptography, this is some library in memory that would be joining every encryption process, and every process can work independently with different containers. So someone is trying to create, to delete, to open, how you arrange it, considering that we have a bottleneck here, reading the smart cards. And when we speaking about different platforms, cryptography is algorithm, but to to make it, you need everything from PowerPC to Windows XP. That's where you need to consider syncing with absolutely different platforms. And then when you can consider dispatching smart cards, so remember about the protection of keys and the difficulties related. So there are some simple considerations that have been around for a long time with the hardware reliability. We cannot completely trust the network adapters. We cannot trust the dispatching memory. And potentially some memory can leak to the network. For instance, take a case that's similar is for Bleak, the vulnerability where the hacker could get some address space of the server. And what's used in the Russian developments, the keys should never be kept openly and never be used openly, and they will never get into the memory. So all the activities will be masked, distributed masks in memory, and so it adds some security here and there. And then the question that Stanislav was mentioning on attacks on third-party channels, that we need to consider the attacks that have permanently been detected, and the multiplication, for instance, should not show the number which we multiply. So let's talk about the key carrier, the key hardware, where you store the keys. We have here many approaches, and in addition to what Stanislav said, we need to be talking about keeping the keys at the common flash drives or in the file system or in the Windows register. Why do we need to support that? But then again, speaking about the life of real users who don't need very high level of security, they will be happy with the KS1 model. And naturally, if they want a higher protection, in particular, if they don't want if they wanted to restrict the number of password guesses, so you can recommend a solution different from a flash drive. If you input the wrong password, they would be blocked. And active tokens are absolutely identical in terms of security to the passive tokens, as once a perpetrator can sniff the traffic between the machine and the card, so there is no difference if he steals the key or if he steals the password and in the next transaction just signs $1 million payment order. But active tokens can be used for extension and additional tools that can somewhat raise the security. One of the approaches is expanding active token to geometric tokens. When we add some additional authentication factor, and after the PIN code, he needs to somehow confirm the operation of the token. And the benefits are obvious. If you lose your PIN code, the perpetrator can do nothing with it, because he will need to input some confirmation. So it can be used in addition in existing system, but then there are downsides. The architecture
Они сейчас кончат уже.
Because you need to consider that we are turning to the tokens and it's waiting, it's doing something. The user can delay with the so these are all issues that you need to address. And then the software in the tokens can be quite complicated, and the verification can be quite cumbersome. So the protected exchange approach. So we have a channel, and it's compromised. And for instance, someone has already broken into it, hacked it, and there's a number of protocols that allow you to get rid of such perpetrators. At the latest conference, we were talking about them. Once we don't want to use additional protocols of interaction with tokens and work somehow in a conventional manner, so we can use another approach, a protocol with a special dedicated server. So the user, now we have three stakeholders, the user and someone and the server, and the user asks the server that he wants to work with the card, then the computer will send all the inquiries to smart card and the server, and after some kind of double-sided authentication according to protocol similar to Hellman, through simplest certificates in a simpler form, CV certificates, after this exchange and protected connection, the server will get some unique information and will provide the certificate for the computer and start interacting with the double with the authentication through the protected channel where you can send files and signatures. This approach is very popular. In particular, it's used in the universal electronic cards, and judging by the latest conferences, it will be used in the electronic passports that we are going to get soon. So very quite high level of security that it provides, and the protocols is quite simple. You don't need to change them. So the downsides, you need the server, you need access to the server, and as you have errors, once they uh, occur, the common user cannot handle them. Even sometimes a savvy user can be quite, in a difficulty. So if we want to use active tokens without any specific protocols, we could use additional tool of security, in particular the protected readers, which are very simple. We consider four sides: a user, computer, the reader, and a smart card or USB token, which would be inserted in the reader. The user will send a document to be signed. It will be hashed. The computer will send the document, and then if the hash will go to the reader will compare the hash from the document with the incoming cache. If it matches, then you can show it on the display with the question if you want to sign it. If the user says yes, it goes to the smart card and gets back. So it looks approximately like that. A user will send a payment order. It will be shown here, and so even if a pin is stolen, so the abstract security level is high. The user can always say no, but you cannot always rely. So you can do that with a smartphone. For instance, if there is a solution and on your smartphone you keep the secret key, and then the protected connection would be established, and some data will be sent, and the user will sign. In case there is visualization, it will approximately look this way. So the user will make a decision if he is going to sign it or not. So the random numbers generator. If you are familiar with cryptography, you know about the generation of random numbers. So again, just like always, when you embed the system, so why should we invent something new? Why don't we take an existing solution? Let's consider the Western solutions. So first, the generator that Stanislav was talking when ANB paid 10 mil for promoting, and that was very questionable. Intel Secure Care, we immediately it is potentially subject to hardware trojans, which can easily reduce entropy of the sequences. And the Windows Linux proprietary, or the entropy is absolutely ungrounded. And I cannot tell you, but looks like it's going to work. So the Russian developers can offer several generators which with different approaches. Hardware gadgets that you can just use and insert, biological gadget, and the interaction with the user. But they are not. They have low speed and are not applicable in every architecture. So we are still searching, and we heard presentations for gadgets, such gadgets, at the recent conferences. And embedding, it's all so good, but how are we going to embed in real system? How can we start using Russian cryptography? Well, not much trouble. because it's out of the box, almost out of the box. Let's talk about Windows. When you install libraries, you will have Outlook encryption and the signature and the documents in Microsoft Word, Excel, and authentication through WinLogon for smart card will work on the local machine, which is safe and comfortable. TLS will work through the standard interfaces, and any user who wants to have good TLS will have the Russian algorithm. So I guess it's all available because Microsoft Windows has modularity, printer. We just connect our libraries, and any application can easily use the local algorithm and SPI interface, where you can use any security protocols. What about Unix? So libraries like OpenSSL and LibreSSL have support. You can use them and include in Apache, and it can be questionable, but they're expandable, and you can write your own engines, and some vendors have them already. And here you can write one code for Windows with cryptography. It will be identical for Unix, but for that you need some processor, because Microsoft is out of the box, but Unix doesn't have it. And there are two considerations here. You can either do it or get a ready one, for instance, Copyright library that does it. How does it work, this cryptography? A person who starts to look at it will see that there's a huge number of functions, but they break down into two classes containing basic functions and heavier functions that allow to use short methods to address many tasks, and allows you to sign with your key some message. Even 10 is not very difficult to use. That's the way you can deploy the Diffie-Hellman protocol for two users. First, Alice is getting her open key, then Bob is doing the same thing, and then Alice and Bob import open keys of each other, and then the exchange key is 2847, and then algorithm, and then these keys can be used for encrypting the session and further activity. So there is some deficiency. Internet Explorer does not cause many issues because it works through the out-of-the-box interface, so it will be working with the set of libraries. Mozilla and Chromium can use Russian algorithms, and because out-of-the-box versions do not have it, you need to support and upgrade. And you can use plugins on modern browsers that reflect cryptography. So, for instance, Cadis plugin that you can use for Google Chrome, Mozilla, and Opera. That's where I'm done. I thank you for your attention. Could you please comment on the vulnerability of Russian algorithm to the logjam, which reduces the Diffie-Hellman key to 512 byte? Simple comment. Yes, indeed. Yes, vulnerability is there, but we don't have a short bit version. So these attacks are not applicable in Russia because in 2010 we didn't have this cryptography made in 2005. We don't have any short key option. So you can reduce some algorithms. No, that is not is not an option. It's not applicable. Thank you. That's it.